You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Machine learning is one of the most important branches of artificial intelligence because it gives systems the ability to improve their performance by learning from data. Instead of being told explicitly how to perform every step, a machine learning system identifies patterns in information and uses them to make predictions or decisions. For example, an email filter does not need every spam message explicitly coded. Instead, it learns from thousands of labeled examples which characteristics distinguish spam from legitimate messages. This data-driven approach has made machine learning the engine behind many of today's most visible AI applications, from recommendation systems to speech recognition. By framing intelligence as the ability to learn from experience, machine learning moves AI closer to adaptive, human-like behavior. The difference between traditional programming and machine learning lies at the heart of this shift. In classical programming, developers write explicit rules. If a condition is met, then perform a specific action. This approach works well when rules are clear and stable, such as calculating interest on a loan. Machine learning, by contrast, does not require programmers to define every rule. Instead, it analyzes data to infer patterns automatically. For instance, rather than writing rules for identifying cats in pictures, a machine learning model learns features from thousands of labeled cat images. This distinction is crucial. Programming encodes human instructions, while machine learning extracts knowledge from experience, enabling systems to adapt and improve over time. Supervised learning is the most widely used type of machine learning, defined by its use of labeled data. In this approach, the algorithm is provided with input-output pairs during training, learning the relationship between them. If the input is an image and the output is the labeled dog, the system gradually learns to map new images to the correct labels. This method is called supervised because the presence of labels provides guidance, much like a teacher overseeing a student. The strength of supervised learning lies in its clarity and directness, producing models that can achieve high accuracy when sufficient labeled data is available. Within supervised learning, classification tasks form a major application area. Classification involves sorting items into discrete categories, such as spam versus not spam in email filtering, or malignant versus benign in medical diagnosis. The system learns from examples in each category, then applies its knowledge to new cases. Classification problems are ubiquitous, appearing in finance, healthcare, marketing, and security. They demonstrate how supervised learning can replicate tasks that humans routinely perform, but at a much larger scale and with greater consistency. The ability to categorize effectively allows AI to transform raw data into actionable insights, making classification a cornerstone of applied machine learning. Regression tasks represent another form of supervised learning, focusing on predicting continuous values rather than discrete categories. For example, a regression model might estimate the future price of a house based on features such as size, location, and age. Unlike classification, where outputs are labels, regression produces numerical predictions. This makes it useful for applications like forecasting sales, predicting energy consumption, or estimating patient recovery times. Regression highlights how machine learning can support planning and decision-making in contexts where outcomes vary along a spectrum. Its strength lies in transforming past data into quantitative forecasts that guide future choices. To ensure that supervised learning models truly learn rather than memorize, data is divided into training and testing sets. The training set teaches the model patterns, while the testing set evaluates whether those patterns generalize to new cases. Sometimes a third validation set is also used for fine-tuning. This division mimics real-world conditions, where AI systems must perform on data they have never seen before. Without proper testing, a model may appear accurate during training but fail in practice. The training-testing process emphasizes the importance of evaluation, ensuring that learning reflects meaningful generalization rather than superficial memorization. Overfitting is a common pitfall in supervised learning, occurring when a model learns the training data too well, including noise and irrelevant details. Such a model performs impressively on the training set but fails when faced with new data. Imagine a student who memorizes practice exam answers but cannot solve variations of the same problems. Overfitting reflects the same issue. It highlights the delicate balance between complexity and generalization in machine learning. Techniques such as cross-validation, regularization, and pruning help mitigate overfitting, reminding learners that effective models must capture essential patterns without becoming overly rigid or narrow. Unsupervised learning takes a different approach, working with unlabeled data. Here, the goal is not to predict specific outputs but to uncover hidden structures within the data. For instance, an unsupervised system might group customers based on purchasing behavior without prior labels telling it which customers belong together. This kind of learning reflects how humans often explore unfamiliar environments, looking for patterns and categories without predefined answers. Unsupervised learning is valuable for discovery, revealing insights that may not be apparent even to experts. It expands AI's role from prediction to exploration, making sense of data in open-ended ways. Clustering is one of the most common unsupervised learning techniques. It groups data points based on similarity, creating clusters that share features. For example, a retailer might use clustering to segment customers into groups with similar shopping habits, enabling targeted marketing. Algorithms like k-means identify clusters by minimizing differences within groups, while maximizing differences between them. Clustering highlights the power of unsupervised learning to reveal natural divisions and patterns in data, often producing actionable insights without prior assumptions. For learners, clustering demonstrates that not all learning requires labels. Sometimes patterns emerge naturally from structure alone. Dimensionality reduction is another key method in unsupervised learning, focusing on simplifying data while preserving essential information. High-dimensional data, like images or genetic profiles, can be overwhelming for both humans and algorithms. Dimensionality reduction techniques, such as principal component analysis, compress data into fewer dimensions, highlighting the most informative features. This not only improves efficiency, but also makes visualization possible, enabling humans to better understand complex datasets. For example, reducing a dataset of thousands of genetic markers into a handful of components can reveal meaningful patterns of variation. Dimensionality reduction illustrates how AI can distill complexity into manageable representations. Reinforcement learning introduces a third paradigm, where learning occurs through interaction with an environment rather than from labeled or unlabeled data. An agent takes actions, receives rewards or punishments, and adjusts its behavior to maximize long-term gain. This mirrors how animals learn through trial and error, refining strategies based on experience. Reinforcement learning is especially powerful in sequential decision-making tasks, such as playing games, controlling robots, or managing resources. By treating actions as experiments and feedback as lessons, reinforcement learning systems become adaptive problem solvers capable of discovering strategies that may not be obvious to humans. Rewards and punishments form the feedback signals that shape reinforcement learning. A reward reinforces successful behavior, while a punishment discourages ineffective strategies. For instance, a robotic arm learning to stack blocks may receive a reward for successful placements and a penalty for dropping them. Over time, the agent learns to favor actions that lead to higher cumulative rewards. This simple mechanism mirrors fundamental learning processes in nature, demonstrating how reinforcement learning harnesses feedback loops to guide adaptation. It shows that intelligence can emerge not only from examples but also from experiences shaped by consequences. A central challenge in reinforcement learning is balancing exploration and exploitation. Exploration involves trying new actions to discover potentially better strategies, while exploitation relies on known actions that yield reliable rewards. Too much exploration can waste time, while too much exploitation can prevent discovery of superior solutions. Striking the right balance ensures steady improvement. For example, a recommendation system might occasionally suggest new products to learn about user preferences, even if known favorites are safer bets. This balance illustrates the dynamic nature of reinforcement learning, where success depends not only on past knowledge, but also on the willingness to take risks. Temporal difference learning refines reinforcement learning by updating predictions based on differences between expected and actual outcomes. Instead of waiting until the end of a sequence to adjust, temporal difference methods allow learning at each step. For instance, a chess playing I can update its evaluation of a position immediately after a move, rather than waiting until the game's conclusion. This approach accelerates learning and enables more responsive adaptation. Temporal difference methods underpin many modern reinforcement learning successes, including systems that master complex games and control tasks. They highlight how incremental learning can accumulate into sophisticated strategies. Finally, it is important to see how supervised, unsupervised, and reinforcement learning relate to and complement one another. Supervised learning provides precision and accuracy when labeled data is available. Unsupervised learning discovers hidden structures when labels are absent. Reinforcement learning thrives in dynamic environments where trial and error guides improvement. Together, these three paradigms form the foundation of machine learning, covering the spectrum of learning scenarios. They are not mutually exclusive, but often combined in hybrid systems that integrate their strengths. For learners, understanding their relationship provides a roadmap for appreciating the diverse ways AI acquires knowledge and adapts to the world. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Supervised learning encompasses a variety of algorithms, each with its own strengths. Decision trees split data into branches based on conditions, producing simple and interpretable models. Support vector machines create boundaries and high-dimensional spaces to separate classes with maximum margin. Neural networks, inspired by the brain, connect layers of artificial neurons that capture complex patterns, making them highly versatile. These algorithms illustrate the diversity of approaches within supervised learning, from the transparent and rule-like to the complex and powerful. Choosing the right method depends on the problem at hand, the available data, and the need for interpretability versus performance. Unsupervised learning also employs distinct algorithms tailored to discovery. K-means clustering divides data into groups by minimizing differences within clusters, offering simplicity and efficiency. Hierarchical clustering builds nested groupings, revealing relationships across levels of granularity. Principal component analysis reduces dimensionality by transforming data into components that preserve the most variance. These methods uncover hidden structures in data, helping researchers and practitioners identify meaningful groupings or simplify overwhelming complexity. By applying these algorithms, AI systems discover order where none is explicitly provided, making unsupervised learning an essential tool for exploration and analysis. Reinforcement learning depends on specialized algorithms designed for sequential decision-making. Q-learning is a popular method where agents learn the value of actions in states, refining choices to maximize cumulative rewards. Policy gradient approaches take a different route, directly optimizing the policy that maps states to actions. Both approaches aim to discover effective strategies, but they do so with different emphasis. Q-learning through evaluating state action pairs, policy gradients through adjusting overall behavior. These algorithms have powered advances in gaming, robotics, and complex control systems, demonstrating how reinforcement learning provides the adaptability needed in dynamic environments. Supervised learning finds wide application in the real world. Fraud detection systems learn to distinguish legitimate from suspicious transactions by analyzing labeled examples. Medical diagnostic tools classify diseases from patient data, guiding doctors in treatment. Spam filters identify unwanted emails with high accuracy, protecting users from constant nuisances. These applications show how supervised learning transforms data into practical insights, supporting decision-making in areas where accuracy and reliability are paramount. The clarity of labeled datasets makes supervised learning especially attractive in domains that demand precision and accountability. Unsupervised learning contributes by revealing structures that were previously hidden. Businesses use clustering to segment markets, identifying groups of customers with similar behaviors. Anomaly detection identifies unusual patterns, useful in cybersecurity for spotting intrusions. Recommendation systems benefit from unsupervised methods that uncover relationships between products and users. These applications highlight the exploratory nature of unsupervised learning, where the goal is not prediction but discovery. By finding structure in unlabeled data, AI uncovers insights that often surprise even experts, providing fresh perspectives on complex domains. Reinforcement learning demonstrates its strengths in interactive environments. Robots learn to navigate spaces by trial and error, improving their movement strategies over time. Game-playing AI systems, such as those that master chess or Go, refine tactics through millions of simulated matches. Self-driving cars apply reinforcement learning to balance safety, efficiency, and adaptability in unpredictable traffic. These examples show how reinforcement learning thrives where outcomes are uncertain and feedback is incremental. Its adaptability allows machines to improve continually, making it a key driver of progress in environments where flexibility is essential. Data requirements differ across learning types. Supervised learning depends on labeled datasets, which can be expensive and time-consuming to create. Unsupervised learning requires only raw, unlabeled data, making it attractive where labels are unavailable. Reinforcement learning needs sequential interaction data, often generated through simulation or real-world trials. These requirements shape which approach is feasible in a given context. For learners, understanding these differences clarifies why some methods dominate in particular applications, while others remain limited to specialized niches. Data availability is as critical as algorithmic design in determining the success of machine learning projects. Supervised learning offers notable strengths when high-quality labels are available. Its models can achieve high accuracy and provide consistent performance across diverse domains. Because it is grounded in clear examples, supervised learning also enables evaluation through straightforward metrics, making results easy to measure and compare. This clarity and reliability make it a trusted tool in fields such as finance, healthcare, and cybersecurity. Its precision shows the power of aligning algorithms with well-prepared data, reinforcing the importance of careful dataset design and annotation. Unsupervised learning's greatest strength is its ability to uncover hidden structures without needing labels. It enables discovery in domains where patterns are not obvious, such as identifying emerging customer trends or detecting subtle anomalies. This freedom from labels allows it to scale more easily in data-rich but unannotated environments. Unsupervised learning highlights AI's exploratory side, where the goal is not to confirm known answers, but to reveal new possibilities. It empowers organizations to extract value from vast quantities of untapped information, often leading to insights that inspire innovation and strategy. Reinforcement learning excels in adaptability, making it uniquely suited for dynamic and interactive contexts. By continuously updating strategies in response to feedback, reinforcement learning agents can adjust to shifting conditions. This adaptability is invaluable in robotics, where environments are unpredictable, or in finance, where markets change rapidly. Reinforcement learning emphasizes long-term outcomes, teaching systems to pursue strategies that yield cumulative rewards rather than short-term gains. Its strength lies in fostering resilience and adaptability, qualities essential for intelligent behavior in uncertain and evolving worlds. Supervised learning faces challenges, including the cost and difficulty of producing large labeled datasets. Labels may also embed human biases, leading to unfair or skewed predictions. Overfitting is another persistent issue, where models learn training data too specifically and fail to generalize. These challenges remind us that supervised learning, despite its strengths, depends heavily on the quality and diversity of its training data. It highlights the need for careful dataset construction and ongoing monitoring to ensure fairness and reliability in real-world applications. Unsupervised learning also presents challenges, particularly in evaluating results. Without labels, it is difficult to judge whether discovered clusters or patterns are meaningful or useful. Algorithms may produce groupings that make statistical sense but lack real-world relevance. Interpretation requires human expertise, limiting automation. Furthermore, unsupervised methods can be sensitive to parameter choices, leading to different outcomes from the same data. These difficulties illustrate that discovery without guidance is powerful but also uncertain, requiring careful validation to ensure insights are both accurate and actionable. Reinforcement learning struggles with inefficiency, as learning often requires massive numbers of interactions. Training an agent to play a game or control a robot can involve millions of trials, making the process computationally expensive. The design of reward signals is another critical challenge. Poorly defined rewards can lead to unintended behaviors. For example, a robot might learn to exploit loopholes in its environment, rather than achieving the intended goal. Reinforcement learning's sensitivity to design highlights its complexity, reminding us that adaptability comes at the cost of careful construction and significant resources. Hybrid learning approaches seek to combine the strengths of supervised, unsupervised, and reinforcement learning. For instance, a system might use unsupervised learning to organize raw data, supervised learning to refine predictions, and reinforcement learning to adapt behavior over time. These combinations allow AI to function flexibly across diverse scenarios, leveraging the unique advantages of each paradigm. Hybrid approaches reflect the recognition that no single method is sufficient for all problems. Instead, the future of AI lies in integration, where multiple learning strategies interact to produce robust and versatile systems capable of tackling a wide array of challenges. Supervised, unsupervised, and reinforcement learning form the foundations upon which advanced AI methods, including deep learning, are built. These paradigms establish the basic ways machines acquire knowledge through guidance, discovery, or interaction. Every sophisticated model or hybrid system ultimately rests on these principles. Understanding their mechanics, strengths, and challenges prepares learners for the complexities of modern AI while grounding them in the essentials. These three learning approaches define the spectrum of how machines learn, adapt, and evolve, making them indispensable stepping stones for deeper study in artificial intelligence. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.